it doesn't matter, and we measure it. And we measure it here on the left-hand side. And the beautiful thing about cosmology is that we think that this is pretty straightforwardly related through, on large scales, just some simple linear transfer function, which we know, I call that delta here, to something which is of deeper fundamental interest, which is a quantum field theory correlators of some metric fluctuations on curved space-time, and necessarily some parts of this object we know about the certain non-perturbative regimes of quantum gravity, okay? So the main thing is that in cosmology, we measure this, and so we should understand quantum field theory in curved space-time. And for me, this is the main goal of cosmology of the early universe or inflationary cosmology, is to learn as much as possible what can we say about this quantum field theory correlators. And so in so doing, we have aspirations of improving our understanding in the future. We already know that thinking about the first fraction of a second of the Big Bang and inflation has already profound implications for our understanding of the laws of nature. We know that it implies that there are new degrees of freedom that are beyond the standard model, and there must be new energy scales, new fundamental constants that do not appear to be coming in the standard model. So there is something beyond the standard model that we have to understand. We know that we can probe gravity at energies that we would have never any hope to probe otherwise. In particular, how does gravity behave at very short distances? Is it still well described by general relativity or by something else? More generally, which kind of quantum field theories are even consistent on a cosmological background? This is such a simple question, and we don't have a good answer yet. If I wrote down a Lagrangian and I put it on a background like the sitter, we don't really know good tests to see if this admits a consistent UV completion. And more ambitiously, perhaps we would like to even understand more profound properties about space-time. And perhaps there is a quantum gravity regime that makes sense in the sitter, or perhaps not. And if there is, what would be its description? Would it be a string theory, a holographic approach? And so to try to tackle, I would not answer all of these questions, but the main approach that we are trying to develop is going into this direction. And so I can tell you what people have been doing in the past 20 or so years, maybe 30, in trying to get there, and why there are some problems. So the main approach so far to primordial cosmology has been writing down models, usually in the form of effective Lagrangians. So Lagrangians usually with one or maybe a couple of scalar fields, and trying to compute their predictions, usually in the forms of correlation functions. And this is very useful to have ideas of what happens. However, after a while, we are now in the situation in which we have very many models, and we have, in fact, too many models given the data that we have. And many of these models have all the same or indistinguishable predictions. So we don't know what to do. Writing more models does not seem to help us making progress at this point. And perhaps the real issue is that theory, our theoretical understanding is so limited, the theory does not give us guidance. Which one of these effective Lagrangians that we write down with scalar fields is actually a promising one? Do they admit ultraviolet completions? Can they be extended to energies in a way that is compatible with the fundamental principles of physics, such as unity and causality and locality, or not? We don't know how to answer that question. So that makes it hard to understand which models we should really take seriously and which we shouldn't. In fact, we don't even know exactly how large should be corrections to quantum field theory. We know quantum field theory cannot be the end of the story because we cannot quantize gravity in quantum field theory. So there's probably something beyond that, but we don't know how large those corrections should be. And so the idea is, perhaps if we try to think about the problem from a different point of view, and for me, this different point of view will be the cosmological bootstrap, maybe we can shed lights on different aspects of the problem. And all of this, I'll try to give you some concrete examples. And most of the examples will be based on studying gravitons and the dynamics of gravitons. Okay, so let me say in just one word what the bootstrap idea is. So usually, the way we do physics, for example, high energy physics, cosmology, or particle physics, is that we start with some ideas of some fundamental principles. For example, if you're writing a quantum theory, you probably need unitarity so that your predictions, you compute probabilities that make sense. You want the theories to be local, to obey some symmetries. And usually, from there, we write down models. We propose models that obey those properties. For example, the standard model or a scalar field Lagrangian for inflation. And then, given those models, we compute observables. If we're doing particle physics, we compute an amplitude. If we're using cosmology, we compute a correlator. And then we use that as prediction. The main idea here of this different approach is that in certain cases, it is more convenient to go directly from these fundamental principles to the observables without writing down explicit models. That is particularly useful in two situations. One is when there are too many models that are compatible with the data, so you don't really know which one to use. And two, when the things you want to try to predict are particularly simple observables. For example, 2-point functions or 3-point functions in cosmology are relatively simple objects. So you might have better chance at trying to predict those without writing down explicit models. Any questions at this point?
I think we're good.
I didn't understand, but maybe you said you're good. Can we move
on? I think we're good. So you can continue.
Good. So, okay. So if I want to do this approach in which I don't write down the model, I have to tell you at least what is the thing that I want to compute, right? What is the observable? Okay. What is the output of this calculation? And so let's discuss what are the natural observables in cosmology. So for the rest of the talk, I'll assume that the very early universe is described by a phase of accelerated expansion that is very close to the sitter, so that such that the space-time is very close to the sitter, so that the metric is the FLRW metric with an almost exponential scale factor. And so I can describe the sitter in conformal coordinate in this conformal diagram. So in this diagram, time is moving up here. And in this diagram, it is this upper left triangle that represents the space-time that is relevant for cosmology. This is the so-called cosmological patch or Poincaré patch. The infinite past is represented by this green line. This is the time going to minus infinity. To some extent, this is what we would call the Big Bang. And then the infinite future, you have to move up, is represented by this yellow line. So mathematically, this line here is the future conformal boundary of the sitter, is when time runs to plus infinity. It's not a physical boundary, it's a conformal boundary. You only reach it if you move for an infinite amount of time. More physically, this boundary should be interpreted as the reheating surface at the end of inflation. So now we can phrase the problem. The mathematical problem is that we want to compute quantum field theory correlators on this surface, and we are going to interpret that result as the correlators on the reheating surface of inflation, which we then use to make predictions for the cosmic microwave background or large-scale structures. The main object that I will use will be a more primitive object than correlator, and it will be the wave function of the universe that I'm going to call psi. So every time you see psi, this is a wave function. It's the same wave function that you use in quantum mechanics. It depends on the variable of the theory. In this case, these variables are fields. I collectively denote them as phi, but phi contains all the fields in the problem. All the fields in the standard model, all the inflatons, all the metric perturbations, all the fields. In the infinite past, I'm always going to assume that the vacuum that we choose is the so-called Bunch-Davies vacuum. This is the vacuum that you would have in Minkowski on short scales. And the name of the game is to say, given that you start with this vacuum, if you evolve in time, what is the state of the universe at this infinite future? So what is psi, the wave function, in the infinite future at this boundary? So that's what we want to compute. Psi is the wave function. So
Enrico?
just like, yes.
Yeah, so I have a question. Could you go back one slide, please? Yeah, there. Yeah, so it's a very naive question. Do you know if there are like some analogies to super translations in that past infinity?
Sorry, analogy with what?
Of super translations in that past infinity. I mean, like analogous to what happens in Minkowski space. I don't know if there are some, so that's why it's a very naive question.
No, I mean, if there was something asymptotic, it would have to be on the boundary rather than in the middle of space. So this is in the middle of space. If you want to find some asymptotic symmetry, they exist either on the future boundary, on the past boundary. These look like boundaries, but they're actually not. When you move here, because you're on the top of a circle, you come back. So this space-time, in contrast to Minkowski, that looks like this space-time here is only two boundaries, which are one is here and one is there. And in cosmology, we only see the one boundary that I'm talking about. In terms of asymptotic symmetry, yes, they do exist, but I will not discuss them much in this talk.
Oh, okay. Thank you.
But they should be, usually asymptotic stuff is discussed near a boundary rather than in the bulk. I'm calling this one, I'm calling the bulk, everything which is inside here and the boundaries. Good, so this is the wave function that we want to compute, is a functional of all the fields in the theory. Just like in quantum mechanics, this would be a function of x. X is the position of some particle when you do the harmonic oscillator, and here we're doing quantum field theory, so this is a functional of all the fields. And I can write the most generic functional as the exponential of a bunch of free coefficient psi n times all possible powers of the fields, 1, 2, 3, 4, n fields. If I give you all these psi n's, then I fully specify the wave function of the universe. Once you know the wave function, you know how to compute expectation value, right? The expectation value of an operator is the integral in all the variables of the wave function operator wave function. So this is a primitive object. When you have it, you can compute everything. For example, if you want to compute the 2-point function at lowest order, is just twice the quadratic coefficient here. For the harmonic oscillator, this would be just the root mean square of the harmonic oscillator. The 3-point function is to linear order related to psi3 here, and so on and so forth. So by specifying all this psi n, I specify all the n-point function of the theory in perturbation theory. So the rest of the talk, I'll only discuss this psi n. And you should think of them as being a proxy, something that is closely related to correlation functions. I hope that's clear, because that's what I'll discuss. If you have questions about that, please do ask. So in principle, we know how to compute the wave function, just like we know how to compute correlators in perturbation theory. From quantum mechanics, you might know that the wave function can be written as a path integral from some infinite past to some state at some time t you want. And the weight of the path integral is e to the I the action. So if you give me a theory of inflation, or you name it, I put the action here into the IS, and I can compute this path integral that gives me the result. In practice, I can only do that in perturbation theory, and we know how in perturbation theory the calculation of a path integral can be written in terms of a Feynman diagrams or Feynman-like diagrams. The theory tells me what interactions F appear on all the vertices, And the theory, the spectrum of the theory tells me what the propagators are. In here, I have propagators that go from one point to another point in the bulk. Now time is running always vertically. But I also have propagators that go from the bulk to the boundary, and those are usually called K. Okay, so once you have a theory, all of these things are specified, and to any given order in perturbation theory, you can compute this object. It might be a bit boring to compute, it might be laborious, but you can. So in principle, this could be the end of the talk, because I told you how to compute the wave function. And just to be specific, for example, a propagator, bulk to boundary looks like this. This is the propagator of a massless scalar or a massless graviton in the sitter. It goes like e to the I kt in the infinite past, so it oscillates like a particle, but in the future it behaves differently. And the power spectrum tells you that correlation functions decay logarithmically or grow logarithmically at large scales. Okay. So the idea is that now I want to try to do something better than just computing this wave function in specific models. I want to learn generic properties of the wave function that do not rely on individual models. So to do that, I'm going to use three things. I'm going to use symmetries and then general principles like unitarity and locality. So instead of computing it in a given model, I'll try to see how these properties constrain the wave function.
Enrico?
Yes. Yeah, I can hear you.
So yeah, there is a question here.
Yeah.
Enrico, so coming back to that statement that you want to avoid thinking about models, is the purpose here to get to results that are valid for any models, or you're making also, you will make assumptions about models like okay, these results will be valid for certain classes of models, not for all sort of models. I'm just wondering this to get prepared for the next part of your talk.
Yes. Yeah, hopefully it will be clear as I go, but definitely I will assume a certain spectrum. So I will assume which degrees of freedom are in the theory. But I will not write down any Lagrangians. But yes, there will be classes of models that I consider. And the main reason why I don't want to rely too much on models, well, is maybe two reasons. One is that we don't know what the right model is. So we have many options. But perhaps more deep question is that to some extent, we would like to learn about the ultraviolet completions of quantum gravity or theories, things that go beyond our understanding. And so for those, we definitely do not have the right model. On the other hand, we know that unitarity should be satisfied no matter what model you write down. So there are certain constraints that are more fundamental, more primitive than each models. And usually those are more powerful when you don't know the model. For things like the standard model, if you want to predict the scattering of the W at LHC, then it's useful to have a model because you know that's a well-tested model. For cosmology, we don't have that luxury. We don't have a very well-tested model of inflation. We have so many options, and we don't really know which one is better at this point.
Thank you.
Okay, so the first thing that I'm going to use will be symmetries. So probably you know from Cosmology 101 that there is a set of symmetry that we observe in the sky. The universe looks homogeneous and isotropic, meaning it's invariant under rotations and translations. And the initial conditions of the universe are also approximately scale invariant. So I'm going to assume scale invariance in the rest of the talk. However, we know that the universe is not invariant under boosts, meaning it's homogeneous and isotropic only in a certain reference frame. In fact, in particular, it doesn't look isotropic from the frame of the Earth. If you look at the CMB, there is a dipole that is 10 to 1,000 times larger than CMB fluctuations. So those are the symmetries that we observe and measure. So the most primitive, the most conservative assumption is to assume only those symmetries. In certain situations, it might be useful to assume more symmetries, and there is a general theorem that says that the only additional symmetry that you can add to the system are so-called de Sitter boosts. They are the analog in de Sitter of what you learned about in relativity, which is Lorentz boost in Minkowski. So you can either take the de Sitter boost or no de Sitter boost. No de Sitter. So you have to decide. And both approaches have been very fruitful and very useful to learn more about the theory. The most phenomenologically relevant one is the one in which you don't assume boosts, because no one has ever measured perturbations in the universe being invariant under boosts. And so that's the most close to observations. But for more abstract question, it might be easier to do calculation in cases in which you have boost invariants. And so both are interesting options. So I wanted to give you an example of how powerful it is to assume more symmetries. For example, suppose that the quantity you want to compute is the 3-point function of graviton perturbations. What I call gamma here is a graviton, and the little plus there tells me the helicity. So like a photon, it can come with plus helicity or minus helicity. And so I can ask what is the 3-point correlation function of 3 gravitons. In general, this is a hard questions, but if you assume a lot of symmetry, symmetry is so powerful that there are only 2 possible results that are allowed by all the symmetries. So this is a result obtained 10 years ago by Maldacena and Pimentel. And they say, if we assume this is de Sitter invariant, even though we haven't observed it, then the only 2 things that can happen for 3 gravitons are these 2 and nothing else. One of the 2 is actually the one that you observe in GR. So this is general relativity. While the other one happens in a higher derivative theory in which the action is Weyl, the Weyl tensor, which is a traceless version of the Riemann tensor to the 3rd power. So this is very interesting, but it's also very limiting because we are assuming symmetries that we haven't seen. So we would like to know what is the most generic 3-point function of the graviton if we allow for arbitrary violation of the Sitter boost, which we haven't measured. This 3-point function, for those of you that are maybe close to observations, would then imprint a certain 3-point functions for B modes in the CMB B modes, B mode polarization. So this is how you measure these 3-point functions. So we would like to have them in case we detect B modes that are primordial, then we want to know what should they look like. So for the rest of the talk, I'll just focus on this boostless theories, meaning theories in which I assume translations, rotations, and dilations. Those symmetries can be implies a specific constraints that correlators need to satisfy. Translations, of course, just means that the sum of the momenta has to sum up to 0, etc., etc. But I will not assume any additional symmetry. And maybe I should mention for those of you that work with explicit models is that all models of cosmology break boosts, and most of them break boost by a large amount. So boost breaking does not need to be slow or suppressed. It just means that the universe is foliated by some inflaton that evolves with time. Okay, so that's as far as we can go using symmetries. Let's see if we can use something else, something more physical. And I'll try to use to see what locality teaches us. So if I give you a correlation function or a wave function, how do you know that it comes from a local theory? What property does it need to satisfy? So first of all, let's see what locality is. So colloquially, locality means that I can do science. In other words, it means that something that happens in a galaxy far away is not going to affect what happens here now. Okay, there is a separation. More precisely, in quantum field theory, locality is the requirement of cluster decomposition, namely that if you write a correlation functions of operator at different points, and then you take these points separated, then this correlation function also factorizes into the product of 2 correlation functions, one here and one there. So far away operators do not talk to each other. In practice, when we write down models, we use a weaker notion of locality, which is what I call manifest locality. By manifest locality means that when we write interactions in a Lagrangian, we always write the product of operators and their derivatives at the same time, at the same point. All of them evaluated at the same point. We never write the Lagrangian in which there is interaction of phi of x and chi of y, where x and y are two different points. Okay, that would be a non-local theory. So since I don't want to write down explicit Lagrangians, I would like to know what are the consequences of this locality for the correlators themselves. And in general, this is still an open problem, which is also a hard problem. But in some specific cases, there is a general answer to this question. So if we consider massless scalars and massless spin-2 particles that I call Graviton, then there is a specific rule that a wave function coefficient psi n has to satisfy if it comes from a manifestly local theory. And the rule is written here in the box. You write down this correlation function as some complicated blob with some external leg. Every external leg has a vector, kn. You define for every vector their norm. Then you write the wave function as a function of those norms, k1, k2, kn. Then if you take the derivative with respect to any of those norms, that derivative should vanish at the origin. This is a necessary condition. If you fail this condition, it doesn't matter where you got this thing did not come from a manifestly local theory. So either you screwed up or the theory you started from was not manifestly local. Okay, this is not the most generic case. I don't know the answer for massive fields, etc. But this is a very useful one because the inflaton is an approximately massless scalar and the graviton is definitely a massless scalar. So this is a useful constraint that every prediction should verify.
Enrico?
Yes, yeah, please go ahead.
Enrico, this third statement you're making in that slide is does it come from the second? Is it that the last equation is a result from demanding that Lagrangians must be manifestly local?
Yes, so the statement is that if you start from the manifestly local theory, then the correlator you compute at tree level need to satisfy this constraint. Is this what you mean?
Yeah. No, I'm just wondering because at the beginning you, well, perhaps I didn't understand the first statements about avoiding assumptions about the Lagrangians. So I was just wondering whether the starting point here for this statement is demanding a certain properties of Lagrangians or not.
Well, it depends on what you mean by the starting point. So if you write a Lagrangian, the starting point is that it is manifestly local. What I'm proposing is that we don't write a Lagrangian and then we should just impose this. So it's an equivalent condition that captures the same physics, meaning locality, but it captures at the level of a different description. So I would not say that I start with a Lagrangian and then I imply this. I would say I never mention a Lagrangian. This is my necessary condition. So everything that I will compute will satisfy this. If it doesn't, I don't consider it. That's my definition of what I mean by locality. You can see this condition to be equivalent to having a local Lagrangian, but it doesn't require it.
Okay, I understood better. And regarding, for example, you mentioned, okay, we here we're not considering inverse of Laplacians. So I guess what you have in mind is that a more general notion of locality does allow, let's say, inverse of Laplacians And then in that case, would you expect modification of the last equation, or would you expect it to?
Yes, so there are very specific theories in which inverse Laplacians can appear, but because of solving for constraints, and those are not included in this. Luckily for us, for pure gravity does obey the manifestly local test as written here. So this test is obeyed by pure gravity and is also obeyed by dynamical gravity and a spectator field. So both of those cases, this must be valid. The only exception that I know is when you have a field that is both backreacting and a scalar. And then we can have this inverse Laplacian that generate additional interactions that are not captured by the manifestly local test. Then you have to work a little bit harder to capture those. On the other hand, those are always suppressed. They're always M-Planck suppressed interactions, so they're always tiny for every practical purpose. So we don't know any cases in which those can be large. They're always, M-Planck suppressed. So.
Okay, thank you.
Good. So already at this point, we can actually get quite far computing observables, even though without doing anything specific. So let me give you a concrete example. And as an example, I'm going to compute for you a 3-point function. And since we have to be, let's try to be as simple as possible, I'm going to compute the 3-point function of a scalar. Okay, that's like the simplest non-trivial thing you might try to compute. And some of you who have studied, who are working on cosmology, maybe have done this calculation using either the in formalism or the Schwinger-Keldysh formalism, or maybe some other formalism, and you have done some time integrals and you have computed a 3-point function and then you came up with a result. Here, I'm not going to do any of those integrals. I'm just going to write down the most generic result that is compatible with all the rules that I have set up so far. I'm going to call these Bootstrap Rules. They are the rules that needs to be satisfied for the result to be reasonable. So the first rule that I'm going to mention is that we are working at 3 level in the Sitter space, and the consequence of this is that psi3 has to be a rational function. Rational function means a ratio of one polynomial divided by another polynomial in the kinematical variables. Okay, so this is the first constraint. The second constraint says that I'm starting with the Bunch-Davies vacuum, and this is an extremely powerful constraint. It says that the only singularities that this function can have, the only poles, the only zeros that can appear in these denominators is when k1 plus k2 plus k3 is 0. Nothing else is allowed. So let me call k1 plus k2 plus k3, let me call it k total because it's the sum. Then the denominator can only be kt to some power. It cannot be any other polynomial because other polynomials would have zeros and no other zeros are allowed. So this is an extremely restrictive and extremely powerful statement, the fact that there is a local theory plus a Bunch-Davies vacuum. Then, okay, well, it is convenient that the numerator now is a polynomial, but because of scaling variance, the order of that polynomial is fixed. The wave function has to scale like k cubed, so the polynomial has order p plus 3. So it's a polynomial of finite order. And now the whole problem of computing the 3-point function has reduced to the problem, much simpler problem, of computing a few numerical coefficient in a polynomial. So for any fixed p, then this is just a bunch of numbers that I have to specify, and that gives me the polynomial. So you see the calculation has already gotten simpler. And at the technical level, instead of using k1, k2, k3, I use this symmetric combination of k1, k2, k3 that I call kt, e2, and e3. You don't need to. You can always write k1, k2, k3. It's just the formula gets a little bit neater when I do that. They're just the norm of the external moment. Okay, so we're almost done. I claim that this is the most generic ansatz that we can make. And there is one thing that we haven't used, which is locality. I told you locality requires that the derivative of this vanishes. So let's do it. Let's write down the answers. The answers is 1 over kt times a polynomial. Polynomial is something that has a free coefficient and then the powers of the variables, kt, e2, e3 to some power with free coefficients. And then we're going to impose this manifestly local test, so locality, that demands this derivative to vanish. I claim that this gives all possible 311 non-Gaussianities for a scalar field to all orders in derivatives. This is the calculation and this is the result. So it's a very different way of computing the result from the way you're used to. For every different p, you should start with a small p. P is the exponent of this k total. For small p, it's easy to do this calculation because the polynomial has a very low degree. And as you increase p, the polynomial has a larger and larger degree, and then you find more and more solutions. Looking at larger p is equivalent to looking at higher and higher dimensional operators when we write down an effective field theory. We always know that there are operators with more derivatives, for example. And this basically gives all the non-Gaussianities that have been computed in the literature for in the effective field theory of inflation, for example, as well as it predicts infinitely many other shapes that have not been computed before. For example, let's see if we choose p equals 0, we find that there are two shapes. One of them is the so-called local non-Gaussianity, which is perhaps the most studied form of non-Gaussianity. And the other one is called the conformal non-Gaussianity. Then when p equals 1, that there are no solutions. When p equals 2 and when p equals 3, we find two other solutions. And those are indeed the leading solutions in the effective field theory of inflation, which is the most generic single field theory of inflation. And so those are the so-called equilateral and orthogonal non-Gaussianity. So we can see that this very simple approach has already reproduced what was known, but now I can keep going to all orders in P, and I will find new solutions at every order in P, and we are given explicit formula for all of those solutions. Let me finally mention that if you're doing a single field inflation, then you also have to obey a soft theorem. The soft theorem in single field inflation sets the coefficient of this first shape to 0. And so only the one below this can be large in single field inflation. Okay, I'm gonna move on to unitarity unless there are some questions. Okay, so now that we have learned, so first we're given a very simple example of a completely different way of computing observables that we kind of knew about. So let me tell you how to do more. And to do more and compute the more complicated things, we have to use unitarity. So unitarity is just colloquially the statement that if you want to make a prediction that makes sense, the probability has to be between 0 and 1. Otherwise, that's not a physical prediction. And so in quantum mechanics, that usually says that the time evolution operator has to be a unitary operator on the Hilbert space so that you can ensure the conservation of probabilities. And we have known for more than 60 years, if I give you an amplitude and I ask you, does this come from a unitary theory or not? Already 60 years ago, we knew the answer to that. The answer is that it has to obey the optical theorem. And order by order in perturbation theory, if it is a perturbative amplitude, you should obey the Katkowski's cutting rules, which are basically just the optical theorem order by order. So if it obeys, good. If it does not, it's inconsistent. It's doesn't come from a unitary theory. So in cosmology, if I give you a correlator or a wave function, how do I know whether it comes from a unitary theory or not? Surprisingly, we didn't know the answer to this question until about a year ago. But now we know the answer, and so let me tell you what the answer is. The answer goes under the name of the cosmological optical theorem. So let's consider the simplest possible case, I don't know, n equals 3. So we have a single interaction, and then the fields go on their way, and then they get measured in the asymptotic future. Then the wave function for this interaction has to satisfy a very specific property. Take the wave function as a function of the external energies, K1, K2, K3, and then add to it itself with a complex conjugate and put a minus in front of all the energies. And a minus in front of all the vectors. Okay, it's a funny thing to do because this K here is the norm of a vector. It's a bit funny to make it negative, but okay, if you think of it as a complex variable, there is no problem. And the statement is that this has to vanish. If it doesn't vanish, that did not come from a unitary theory. It's a powerful constraint. Okay, so this is the statement for simple interactions like this one. Since this particular combination of psi of k plus psi star of minus k, this comes all the time. So it's, instead of writing it all the time, let me give it a name. I'm just going to call it disk of psi. This very specific combination, psi of k plus psi star of minus k. So now I'm going to show you how to generalize this condition to all orders in perturbation theory. Any number of loops, any number of fields, of any mass, any spin. Okay. Yes.
Yeah, could you go back one slide? Yeah, so I have this, well, very basic question. Does this discontinuity operator have the same interpretation as in quantum field theory, or the interpretation is different?
Which interpretation in quantum field theory?
Can you say that again?
Can you be more specific? Which interpretation in quantum field theory do you have in mind? Discontinuity just is the variable of a function from one side of a line to the other side of a line. That's usually what's called a discontinuity. It's like a mathematical property.
Okay, okay, so okay, well, thank you, I understand now.
Meaning in quantum field theory, do you have a specific context in mind?
Can you say that again?
In which context in quantum field theory have you seen this discontinuity?
Oh, yeah, like in the usual, well, in Peskin's book, you can see that you can apply some discontinuity through the S channel. It's sort of like doing S, the Mandelstam variable, plus I epsilon. So in that context, I have some discontinuity.
Yes, it's similar. Usually the discontinuity for amplitudes is defined, A of S is defined to be A of S plus I epsilon minus A of S minus I epsilon. And that tells you the discontinuity of the function A as you come from this side and you come from that side. If it was a continuous function, then there would be no discontinuity. And if it is a discontinuous function, then there is a discontinuity.
Yeah, so I had that in mind. So in this case, it's similar, or?
Yeah, it's somewhat similar, yes.
Okay, okay. But you're not applying like the I epsilon prescription here.
Well, there is an I epsilon prescription. But the easiest definition is the one I've given. If you want to put a factor of I, you can get an I epsilon prescription.
Oh, okay, okay.
So I think I can tell you more, but I think the easiest way is to write it as I've written it. And I could tell you more, I could put a star here and put an epsilon, but I think that would make the formula more complicated. So
Okay.
I think it's easier to leave it as is.
Okay, thank you.
Yeah, no, thanks. Okay, so for general diagrams, the rule generalizes as follows. You take the discontinuity, for example, of a 4-point function, and this equal to, you write down all possible cuts of internal lines. There is only one internal line, so there is only one cut. And a cut means that you take that line, cut it in half, and put the remaining two sides to the boundary. Now this becomes the product of two 3-point functions, psi3 and psi3, and you take the discontinuity of each one of them. And then for every cut line, you put a factor of the power spectrum. And the claim is that this should always be the same thing as the left-hand side. And this is not just true at 3 level, but it's true to all orders in perturbation theory, any number of loops. So if you have something complicated, you sum over all possible cuts, 1 cut, 2 cuts, 3 cuts, and then every cut you put the line on the back, you put the line on the future. And then you take the discontinuity of each one of these terms. And then left-hand side and right-hand side have to agree. And this has to be valid to all orders in perturbation theory. So it's very powerful. In fact, it's so powerful that it's valid for any field of any spin and any mass and any interactions. And it's not just valid in the sitter, but in any FLRW. So it's very general, as you can tell.
Enrico?
Yes.
Can I ask a question? So I understand that you're talking about this psi-n coefficients because it's a convenient language, but if you want to talk about the actual correlators, is it so easy to derive these cutting rules at the loop order, or?
Yes,
I mean for example, yeah.
we have not written it down because so in perturbation theory you can always go back and forth. The problem is that the formula gets a little bit messy when you go to very high order. And so we try to take our rules and convert them to rules for correlators, and the formula just got very messy. So we couldn't find like a nice graphical rule like the one I've given you here that encompasses it. So to any given order, I can tell you what the cutting rule is for the correlator, but to high enough order, that rule becomes more and more complicated, which is why we have just used the wave function. So it could be that there is a smart way to rederive the whole thing directly for correlators, and we have not been able to find it.
I see, okay.
But for example, in the paper, we write this expression also for the correlator. The discontinuity of B4 is equal the discontinuity of B3 squared. We write this expression for the correlator. But for loop diagrams, it was getting very messy. I'm not saying that it's not possible, it just the expression was very long to write down in the paper.
All right, this I think we tried a few things with some of the students here, and it is a bit messy indeed. So that's why I was asking. But yeah, I understand.
Yes, I can tell you more ideas that I have on how to do that.
Yeah.
But yes.
I mean, maybe later.
Yeah, at the end of the talk, I'll tell you some ideas on how it might be easier or harder to do. It's useful to do it for loops, because for loops, this allows you to compute loop diagrams without ever computing a loop, because now the discontinuity of a loop, you have to cut a propagator and it becomes a 3-level thing. You can see when you cut it, it's 3-level. And it's easier to compute 3 levels. And for example, we used this to compute the one loop corrections to the power spectrum, for which only one of these coefficients was known. And now we computed it for all the coefficients in the effective theory of inflation, which was not known before. And the calculation was simpler than computing the full loop. It only gives you the discontinuity, but from that, you basically know what the result is. Okay, so let me move on and finish the talk on one more applications of unitarity. So I've already took, yes, please.
There is a question.
Regarding that exact statement that you just made, did you compute the full one loop contribution to, let's say, the power spectrum, or is this just part of it because of the discontinuity function?
Yes, very good. So we only computed the discontinuity. So let's say psi2 is equal to sorry, I was writing down that k cube times some constant plus log k. So what the discontinuity picks up is only this coefficient b, because the discontinuity of the first term is 0. So if there is any corrections to the overall normalization, we don't pick out. But if there is a correction to the log k, yes, because log of k minus log of minus k is equal I pi, and so that comes out exactly from the soft theorem. Sorry, from the cuts. So we don't compute the full thing, but just the coefficient of the log. But if you know that the only thing that can happen is a constant plus a log, then this computes the coefficient in front of the log. So to compute the full thing, you have to be a little bit smart at knowing what the type of logs that can appear. And if you do, then you can compute the whole thing. And here we go into the issue of how do you regularize this correlator, and the way that Weinberg did the loop for the first time was probably correct for spectator fields, but probably incorrect for zeta. And then there was all these discussions of secular divergences, and Senatore Zaldariaga saying that instead of log k, this should be log I log h. And that's a discussion that I'm happy to have. But the short answer is that this computes only the coefficient of the log.
Excellent, thank you.
Which is kind of the only interesting part, because the overall normalization, you don't know it anyways. But very good. So you can do this, but you can do more with unitarity. And just in the last 5 minutes, I'm going to show you another thing that you can do with unitarity. And it gives you something in a simple way, a very surprise, what for me was a surprising result. So suppose now I want to compute a correlator. Then I have to do this integral of the wave function squared times the product of fields. And to leading order, this is just going to take the psi-n coefficient plus psi-n star, because wave function here and wave function star here. So psi-n plus psi-n star. With a minus on the momenta, because there is a star on the phi's. Good. So this is a contact correlator, like any endpoint function will have this form, contact level. Notice that this particular combination is very similar, this combination here, to the combination that appears in the cosmological optical theorem. The only difference is that here there is a minus k, and up there is a plus k. So if you had ever a case in which psi-n is an even function of k, then you can forget about this minus sign. And then this tells you that this combination is 0. So you can already conclude that anything which is even in psi k to minus k cannot appear in the correlator. And that's an extremely powerful result. Now I'll show you that there are infinitely many things that could appear, but they don't because of this. And so in the interest of time, I'm going to show you just the relevant case, which is the 3-point function of graviton, the parity odd 3-point function of gravitons. Okay, so now let me consider, in fact, it doesn't have to be a 3-point function, any endpoint function. Let me consider something parity odd. Parity odd means that there is an odd number of derivatives. For example, 1 derivative, 3 derivatives, 5 derivatives, and so on. So it's parity odd, there's an odd number of derivatives. Okay, then I'm going to write down for you all possible terms that could appear here. These terms I haven't discussed very much. They are IR divergent terms. This is the term that I've discussed before, a polynomial divided by kt to some power. Now, the crucial point is that since there is an odd number outside, and the whole thing has to scale like k cube, the order of the polynomial is 2 plus p. So 2 plus p divided k to the p is always an even function of k, because the overall scaling is like k squared. Because the p cancels, and this is like k squared, and so this can never contribute. So it does not contribute to b. It cannot contribute. So we already discovered that parity odd endpoint function cannot have poles, because these are the only terms with poles and they do not contribute. In fact, this is also even, so it cannot contribute. This term here doesn't satisfy the MLT because it's a linear function. So the first derivative cannot possibly vanish unless it's 0. And in fact, you can easily prove that this also doesn't contribute and this doesn't contribute. So at the end, the only two terms in this expression that are allowed to contribute are these two terms here. Everything else is not allowed either by unitarity or by locality. This is extremely restricted. Look, this term, there is only one because it doesn't have an arbitrary polynomial in front. It's really k cubed times this and nothing else. And this term, there are two of them because you can write two different polynomials in front. And this is all that can happen. So this is extremely remarkable, and there are many fewer options than you would have supposed. So first of all, we have proven that it cannot be KT poles. And in fact, by writing down all those possible polynomials, we can write down all possible 3-point functions. So let me give you the result directly. So the 3-point function, let me be specific and consider the plus 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 helicity. It's easy to write down all the other helicity, but just for concreteness. So the coefficient is just the polarization tensors. This is dictated by little group scaling. And then there is a function. So the goal of this is to write down this function. For technical reason, it's easier to write the result in terms of spinor helicity variables, this 1, 2, 2, 3, 3, 1, and this function h. If you don't know what spinor helicity variables are, forget about h, forget about this, and just imagine that we have written down this overall factor and we are going to try to constrain this psi trim. This psi trim has to obey the MLT and it cannot have any KT pole. So it's only a polynomial of second order that has to satisfy some constraint. And it takes 1 minute to sit down and find all possible such polynomials, and there are 3 of them. 1, 2, and 3. So the correlators of 3 gravitons that are parity odd can only be these 3. Nothing else is allowed. Notice here I cannot put KT poles. So the polynomial upstairs are very simple polynomials. They can only be polynomials of degree 3, 3, and 3 here. And there are only a few polynomials with such property. This is infinitely simpler than writing down a Lagrangian. If you had written down a Lagrangian, you would have found that there are infinitely many interactions. Any interactions of Riemann tensors contracted with epsilon, in principle, can give you a parity odd graviton 3-point function. And if you write more and more derivatives, you get more and more interaction, and you spend the rest of your life calculating the 3-point function for all those interactions. And in infinitely many years, you will realize that you only ever get either 0 or one of these 3 results. So this is very hard to see at the level of the Lagrangian, but it's very easy to see from unitarity. So you would have expected infinitely many, and instead there are only 3. So the Lagrangian is in some sense infinitely degenerate. It's giving you a lot of things that do not contribute to the 3-point function. They contribute to higher point function, but not to the 3-point function. The same happens if you look at a scalar tensor 3-point function, or scalar tensor 3-point function. And we did that analysis in the paper. So we have written down all of them. For scalar tensor, there is only 1. And for scalar tensor, there are 3. Okay, so also relatively simple, and you can see none of these has KT poles either. So they're very simple functions, and they just fit in a line. And this is true to all ordering derivatives. So you can see it's something that would be really hard to find from writing down all of the operators explicitly. If you want to do some CMB analysis, well, you can plot these shapes, and each one of these gravitons, which are this, this, and this, they have a certain shape. And using the standard linear transfer function for B-mode polarizations of the CMB, you can map this into a 3-point function of B modes. And we are proposing that this should be major targets for CMB observations if we were to see primordial gravitational waves in the CMB. Then this should be one of the first tests to be performed, that they have a 3-point function of this form, since this is a very predictive framework. There are only 3 possibilities. If instead you look for parity even stuff, then there are infinitely many. So this simplification only applies to parity odd 3-point function. At the model building level, and this is my last slide, I know it's a bit late, you can ask, okay, well, you never wrote down a model. Are you sure that these things actually do appear in concrete models? And we checked, and the answer is yes, as you would expect. For example, if you write down general models in the class of solid inflation, you can see that all of these correlators do appear. In the EFT of inflation, actually, of those 3 options, only one appears, only very specific linear combination of those functions. And the reason is because there are additional subtheorems. Okay, at the phenomenological level, if you're doing CMB stuff, the largest signal to noise is a scalar-scalar tensor. And that's kind of obvious because scalars have a larger fluctuations than tensors. So you want to have as many scalars as possible. So that's the first one you should look for, is a TTB or EEB or ETB type thing with 1B mode and all the other scalars. Okay, well, let me come to a summary of this discussion. So we have made huge progress. All of this is like all of these general rules for unitarity and locality. We only came up in the last couple of years. So there is really a lot that we still need to do. Now we have some interesting and powerful constraints, both from locality and from unitarity. In terms of this locality, this manifestly local test, and unitarity, this optical theorem. And they can already be used to bootstrap stuff without doing the standard calculation. So one thing that at the end of the talk justifies the title of the talk is that notice I never did a time integral. I never wrote anything with time. All the calculations were all done on the boundary. So time completely disappeared from both the description and the calculation. And we found some surprising results. For example, that there are much fewer 3-point functions than you would. Okay, finally, this is just the beginning. I mean, these are some simple results that one can find, but I think there are more ambitious stuff that is still awaiting to be discovered or figured out. For example, what are positivity bounds for cosmology? What are non-perturbative quantum gravity effects for cosmological correlators? Can we have like a numerical bootstrap that computes things non-perturbatively? All of this has been done in neighboring fields, for example, for amplitudes or quantum field theories, but not in cosmology. So there is a lot to be done. Thanks for listening.
Okay, thank you, Enrico, for your really great talk. I think we have time for some questions. So if anyone has one, please go ahead. Although I have to say that we have some audio problems, so we will not be able to hear you, Enrico, until the end of the question, just to avoid audio loops. So here.
Enrico,
okay, yeah, go ahead.
Okay. Is there any hope to make statements about tails of distributions within this framework?
Yeah, well, hope there is for sure. I think that all of this that I've presented today is perturbative. So I think it will not be very useful for the tails in its current formulation. However, there are several non-perturbative results that that can be written down. And mostly they concern positivity of certain quantities and are non-perturbative, so that there is no expansion here. It's really the integral of the full tails of the full distribution. And these are, I know them for the full 2-point function and for the full 4-point function. So it would be interesting to see if that technology can be used. So to some extent, I would say yes, it's clear that unitarity is relevant for the tails, because what the unitarity tells you is that the wave function has to fluctuate in such a way that the real part and the imaginary part fluctuate in a precise way to maintain the normalization. And this is true both on the top as well as on the tail of the distribution. So that tuning is always needed. But we have not written it down, how that works. So I think it would be interesting to think about it, but I do not have anything close to a concrete answer at the moment of how to do that.
But just a comment on that. I mean, the objects that you use in the language that you use are perturbative, right? These psi-ns, these kernels are by definition perturbative. So in order to answer non-perturbative questions, do you think that you have to use different description? I mean, I completely agree that the fundamental principles are non-perturbative statements, have nothing to do with perturbation, but
well, I mean, the definition of the object per se is not, strictly speaking, perturbative. I mean, I understand what you mean, and I think you're right in spirit, but so the object that I'm studying are the, sorry, I'm not sharing the screen. Let me share the screen for a second. So I can. So the object that I'm studying are these psi-n coefficients, no? And so those have a fully non-perturbative definition, meaning if psi is equal the exponent of minus sum of psi-n phi to the n, this is my definition. I can always non-perturbatively define an object which is the nth derivative of this, evaluated at phi equals 0. So this object does not require any perturbation theory to be defined. This is my definition. I agree that that mostly captures the property of the wave function near the top, but in principle, the definition is a non-perturbative definition. I'm not doing perturbation theory on either side. Now, it is true that probably this is not a very powerful way to characterize the tails, so I should probably do something else. Yeah, it's a good question. I don't think I have a good, better way, but I think that a lot of the steps can be done non-perturbative. Then when I get to calculate something concretely, I do it perturbatively. But these derivatives can be computed non-perturbative. The problem is that when we talk about the tails, most people are interested in just a very rough property of the tails. They usually, instead of computing, so now I'm interested in a very rich object, which is an object that depends on this full function. For every configuration in space or in Fourier space, I have a different probability. usually when people talk about tails, they have in mind primordial black holes. And for that, they look at a much simpler object in which they look at phi at a single point. And they only care about the endpoint function of phi at a fixed point, not as a function of x. So this is a much somehow simpler object. I don't have any k or any x appearing in some sense. Yeah. So I cannot play around with this analytic continuation in energy and in momenta. All of that is lost because I'm looking at a simpler object. And then people even just look at the integral in d phi from, I don't know, some boundary to minus infinity. So it's even less detail. So okay, usually you have more constraining powers from the bootstrap when you have some kinematics that you can vary. For example, the momenta. But here there is no kinematics. There's just phi. So it's harder to think of what you could do. But it's worth thinking about it. I don't think it's a lost cause.
Okay. Any more questions? So we here have one. Go ahead.
Okay, so first of all, thanks for the talk. It was very nice. I really enjoyed it. I was wondering if it's still possible to do bootstrap approach if we drop some assumptions such as scaling variance. Is it still possible to do some calculations? And in the case of considering a non-bunch Davis Bacon, like an excited state, for example.
Yes, I think they can both be done, and it has not been done. So I think both of them would be a fun project. So let me talk about first no scaling variance. So first of all, there's something that I always say is that if I tell you that an animal is a dog, then you know what animal it is. If I tell you that an animal is not a dog, you don't know what animal it is. Yes, it's very vague. You only know it's not a dog, but it could be anything. So when you say no scaling variance, to make some progress, you have to tell me something. I don't want to know what it is not, I want to know what it is. So you have to tell me something about how scaling variance is broken. So I think to make progress on this, you have to say something. Is it weakly broken or strongly broken? If it is strongly broken, do I have some other organizing principle? If you only tell me that there is no scaling variance whatsoever and anything is allowed, I don't think that there will be any concrete progress that you can make because there are too many possibilities. Like now this psi becomes an arbitrary function. It doesn't even have to be a polynomial. Hell breaks loose. On the other hand, if you tell me it is weakly broken and I know the amount of the weakly broken, of the weakly breaking, and I treat it perturbatively because it is a slow roll parameter that it is an s-1, then I think you can make much more progress. So then we can say, okay, then the endpoint function usually scales like 3, but now has to scale 3 plus some weak breaking. And then you can try to play games perturbative in this delta. So I think that would be very interesting, and it has not been done. But you should have the correct expectations. You're not going to be able to describe this kind of potential because the breaking is completely arbitrary, so you're not going to be able to. You have to tell me something like a slow roll expansion. Yeah, just a second, I'll be back. And sorry, and the other question was about, sorry if it is too long. The other question was no bunch Davis. Same answer there. You have to tell me if it is not bunch Davis, you have to tell me something about the poles. Mostly here, the question is going to be is what are the singularities? So what Bunch-Davies was telling us was that if I have general endpoint functions, the only singularities could be partial energy singularities. For contact diagram, this is only KT, and otherwise you have left, right, etc., etc. If you want to have a modification of that, you have to tell me what deviation from Bunch-Davies you should allow. And I can already imagine a simple one. Suppose that is the initial condition, the initial state, instead of being Bunch-Davies, is like A dagger Bunch-Davies. Okay, this is a kind of some stupid initial state in which there is one particle with momentum p that you have decided. I think for this case, you can run the whole program. Now the singularities will appear, not when KT is 0, but when KT matches the momentum of these particles, which now comes in from the initial state. So I think you can do everything I said today for this state. For more generic deviation from Bunch-Davies, you have to be specific about what you have in mind. For example, an interesting class are these Bogoliubov transformations. Those might be slightly more complicated, but I think they're doable. So I think that's a good idea to pursue.
Thanks.
Okay, I think we're good on time. So we had a lot of excellent questions and excellent answers. So let's thank again Enrico. And thank you everyone for coming today. Have a great rest of the day and hope to see you again in the next seminar. Bye everyone.
Okay, yeah, bye, thanks.
Can you show me? Okay, let's go. Where are you?